we're going to talk about automated testing with open source hardware. So, quick introduction. The who part is quite easy. We're Codethink, we'll talk about that in a second. Why? Well, hopefully everybody here thinks that testing is a necessity for good software, and that when you have testing, automating it is even a better idea. So, as a consultancy group, we're often testing software that gets deployed to an actual... Oh, we've got more people coming in. Hello, more audience. So, as a consultancy, we're often testing software that is deployed to hardware. So we'll go through a bit about some testing overview, virtual versus real testing, some open source tools to run your testing, and our journey through to actually why we ended up making some real-world testing tooling. So, quick bit about Codethink. We're open source software experts, or at least that's what our marketing says. We've been enabling customers open source innovation for nearly 16 years. So, I've been around the open source for a long time. So not only do we do work for hire, we're also involved in various open communities. So if you've heard of the ELISA project, that's focusing on safety in Linux. And we're also involved in a lot of long-term maintenance projects, such as a civil infrastructure project, which is another reason why we think testing is good, because obviously those projects need good testing. So, about the speakers. So I'm Ben, kernel hacker, system software expert. I also like doing electronics. And here we have my colleague Mudit.
Hello.
He's also one of our software engineers and another electronics expert. He also likes embedded systems. I mean, who wouldn't? So, we said already, testing. We all need to test our software to ensure the quality for everybody involved. There's been a lot of work around automated testing, and we're going to talk about the tooling we're going to do and why this is useful for reducing the need for manual tests. So, as a software consultancy, we often have a quest to improve software quality for everybody, and through continuous integration and testing, we think that's the best way to go. I mean, humans are not the best at testing things, and it's very difficult to actually clone the best testing people. So, manual testing is difficult to apply to fast-moving projects. So things like Linux kernel, where you've got a lot of code, is difficult to do manual testing on. We can improve the granularity. So often we found that manual testing involves people, and often this is only done on a branch merge or something similar sort of time frame. If we can automate even some of the tests, we can get down to like pre-branch merge or even per commit testing granularity. This, we found, often improves the software experience because we get the errors earlier. We've also found that in the manual testing that you may not always spot mistakes. So testers may not have complete knowledge of different languages. So, and as mentioned earlier, certainly with long-term projects, repetition of testing gets to the point where you just can't keep doing it manually. So, I mean, we're going to talk about automated testing on hardware, but we decided to have a quick say about the virtualized. So you can use emulators such as QEMU to emulate most of your hardware, but the first issue is generally complete accuracy. You may not be able to model your hardware, or you have a complex setup. So often we find when customers' products need to talk to something other like a phone, those cannot be easily emulated by anything currently. However, it is also easier to scale your virtual testing, so it can be part of a testing cycle. It might find some basic errors, and it's easier to integrate into your CI. So you're also going to need testing tools, so part of that is going to be the software. So OpenQA is at the heart of projects such as OpenSUSE. They use it for installation testing. It can do screenshot matching, input event, so it allows testing from your first boot all the way up to actually functioning desktop. So you can use it to test things like, does your desktop have a movie player? We've used it in conjunction with real hardware to provide very similar testing of, does the customer's UI work? So that's something we talked about at FOSDEM last year, and the talk is available, a link in the slides. So Lava, that's something that Linara have built for doing test scheduling and test frameworks. This is often used in projects such as kernel CI. It can be used for scheduling and capturing tests. So, very quick introduction to testing. So now we'll go through some work with actually building our test setups. So we're going to be looking at how we will make a hardware test rig and give some overviews of the type of hardware you can use to control items in that rig. So things like relays, things to control direction of hardware connection, like hardware muxes. We've got specialist network bridges and I/O capture, so things all the way from simple logic analyzers up to something which will capture images. We can't go through all of these, obviously, but the beauty of a lot of these open source projects is that there's so many to choose from. And as I think we'll go through in a bit, it's becoming a lot easier to build these systems. So we can use relays, which are simple electrical controls, to do things like simulate a power button, control power through the system. There are also open source software tools that allow you to control power delivery units. So things like from just a simple plug relay unit that you might find from a shop all the way up to data center control. PDU daemon generally allows you to do that. And of course, if you really want to annoy your fellow developers, you can make clicky noises. Very good. I didn't put a picture in here because generally there are so many variants of relays that it's difficult to choose. They're not always open source, but the software to control them is often. And you can make your own, but generally they are so cheap and available nowadays that you may as well just buy something off the shelf unless you need anything really complex, when of course you can go and make your own thing. So a lot of systems now have some sort of networking, so you can either have Ethernet or in this case CAN bus. So CAN bus is very popular for automotive and some other industrial. And here we have a USB to CAN bridge that somebody has built. It's called the Cannibal. Again, seem to be that bad puns are obviously rife in this area. So this example would be used to say if you needed to inject control messages into a test system, if you're doing, as we do, a lot of work around the automotive. So very useful for that, and you can also use it to listen for messages as well. Again, that's just an example of how some sort of specialist network can be used. This is one I'm quite interested in. So micro SD cards are very useful for storage. You might, as part of your test, want to reflash a new image. So at the top is an initial version of the Tizen SD card mux. I believe when I actually got through reading all the documentation, it says don't use it. Apparently there was problems. But they produced a second version, so The one on the bottom is a micro SD card MUX. I don't think you can't, the micro SD card is underneath it, but it has basically a little micro SD-like connector, so you can plug it in and switch between having the micro SD card connected to your device or to a USB to SD bridge, and you can then just reprogram it, which is great if you want to put a new image on the system. Lastly, so for higher speed systems, this is the Yuzuki HDMI capture board. So HDMI comes in, it gets copied out and to a capture device and to USB-C. So again, this is a thing you could just download and make yourself. So how could we put this stuff together? So this is a very simple test rig that we've been using to test a Sci-Fi unmatched board. In this case, at the top is a Raspberry Pi. We find this is often the best way to isolate the system from our main network, and it means that you can put test images on, use a USB network to connect to the board, USB serial for the console, and if you can just see up there, there's a USB relay board taped into the case. That allows to control the power and reset switches so that if you need to reset or power down the board, you can just flip it through. This one has been thoroughly developed and has had its USB slot fixed. I can recommend that some software engineers are not allowed near boards. So in this case, we use this as part of our kernel CI. So we're involved in testing kernels. So the CI system downloads a new kernel, builds it, installs it, does all the necessary resetting to get the output, and then runs some validation tests to see if, firstly, does the board boot, and then if so, can you then log in? So I'm not sure if we've actually found any major bugs during this, but we found some issues around PCI initialization and stuff like that. So this is more of a more complex system we've done for a customer. This test rig has a lot of things like CAN, other specialized stuff. We connect it to, again, something like a Pi to control it, control all the inputs and outputs, run up our software, get the test back from it. Our test people wanted to show a little bit of the test infrastructure, so we start from some software through a GitLab runner, Docker container with the OpenQA client, so it gets some tests, initiates some tests on the thing, gets some results. So for this customer, this is one of the examples of people who were doing a lot of manual testing, and we have much improved their experience by automating this all out. So what have we got from our experience of doing this? So if anybody's been doing electronic design, a lot of modern systems are now using high-speed signaling, often high-speed differential signaling. This has some issues around the limitation of parts available to do whatever you wanted. We'll explain that in a minute. There's also issues around doing layout. So one of the things we found with the later KiCads is that the layout tools have got a lot better. So matched length routing and things like that. It puts lovely little squiggles into your board, and we'll show some of that later. So we'll show you something we've designed with some modern design tools like KiCad in the next section. Even though you might have an open source product, some of the protocols involved in the projects we've been involved with are not open. Well, sucks to be you. You're going to end up implementing your own stuff there. Even worse, your customers may use closed protocols with even the strangest of connectors. If anybody's done any work in the automotive world, they absolutely love a proliferation of different connectors. And even something that looks like its little cousin, it might be a different color, which means it's a different mating. So that just makes it even worse. Also, there's industry-specific protocols, well, almost. So things like broad reach are often only found in automotive, which means that you either have to do your own thing or buy somebody's expensive solution. So that sucks even more. And this comes to one of the big problems we've found when actually trying to do this sort of stuff is availability of parts. So we had a customer with an automotive Ethernet. We wanted to do 100 base T to automotive connection. And we were initially just going to buy something off the shelf. We looked around and there was nothing. Everybody who even had a vague product said, no, can't buy them. So we thought, great, we'll do something ourselves. And then we ran into exactly why this was the case, because anybody who sold a converter chip for this protocol didn't have any. There was none in stock, and they were quoting lead times in months. So that is one issue that open source is not going to get around for you. So at this point, we've gone through some of the overview, some of our experiences. This has led us on to actually a more successful project that we've done, where we've gone from there's a specific need and we've gone through and actually created something. So at this point, we'll hand over to Mudit.
Right, thanks, Ben. So I think by now we all can agree on the fact that testing is necessary. There's no two ways about it. First, critically, automated testing is crucial to make sure the reliability and safety of our products, as it helps us save time and resources in general, like time is money in that sense, and making our test equipment and entirely our test hardware more accessible, and having test reproducibility. That's quite key. So most of us here are already aware of the importance of testing. I mean, if you've worked with tech before, we all know how crucial testing can be. And as a consultancy, we get to work with various customers and examine different software infrastructures, and we observe a common pattern. So whenever a customer wants to develop a product, majority of the resources are spent on development, and testing infrastructure is usually an afterthought, something always on the back burner. So having various product-based clients, we have understood the genuine underlying reason behind it, which is the focus and priority of a customer or the client to have a working product. So we know tech move fast, and companies want reasonably quick turnaround times, which tempts companies to use quick-to-set-up test methods like manual testing. Quite quick to set up, right? Like you just employ people, have your test rig set up, and tell them what to do, and they do it. Quite easy to set up. They also end up employ solutions that are quick to hack together and reasonably cheap, but for small-scale execution. So once you have, in the general product development lifecycle, the design happens, development happens, testing happens quite quickly, and then release happens, right? Now, after release, we've hacked together this test infrastructure. Now, that test infrastructure remains the same, and the entire dev team, after release, goes to work on the upcoming new feature. Now, after that new feature, people start to work on a new feature, they again have to go to the test infrastructure again, which was hacked together in the first feature. And what does it lead to? So this constant neglect of the overall weak test infrastructure will end up with a testing strategy which is hard to maintain, expensive to run, but will also be expensive to replace with more and more effort that gets put into the initial weak testing infrastructure. So at Codethink, we've had many clients who have found themselves in similar situations, and we saw a recurring issue with testing software and hardware integrations. So here's an example of a test case. So we had a client, automotive client, who were employing a testing methodology where they had testing room with many rigs, and they had 17 engineers with a spreadsheet, and iPhones, thumb drives, and Android phones testing our Apple Pay, Android Auto, and just making sure if everything works and making sure they tick on the spreadsheets if things are connecting or not connecting or whatever they have it. So we were like, well, we all can agree that this is not a scalable solution at all. It will not scale well. So we were like, well, we can definitely solve this problem, but as Ben already mentioned, the existing hardware that exists either is not firstly something that we can automate, or it's very expensive. It has all the bells and whistles we do not need, and ends up being quite expensive. So we were like, well, we'll find something that already exists. So we could find switches, USB 3 switches, which were manual with a button on them, not something you can programmatically control. So what we did was we bought a few of them, right? We ripped off the switches from them, the buttons on them, and we use a microcontroller to interact with them and have a workable solution. So we just about managed to automate the process. But, that is something that you don't put on rigs that are just going to be shoved at the back of the room somewhere. So we're like, we could actually use this, you could see this is an existing issue. We've seen this with various other clients, and we were like, we can make something more robust, which not only helps our existing clients, but also it helps us help the community in general. So we built our own USB switch. Show off. So what does it do? Essentially, it's a USB-C switcher, which helps you connect one peripheral to multiple hosts, or connect one host to multiple peripherals. It's USB-C and bidirectional. So on the product diagram on the right, you can see that we have DFPs, UFPs. First of all ports are USB-C. DFP stands for downward-facing port, which is usually the host port. And we have the UFP, upward-facing port, which is usually the peripheral ports. You can send AT commands over the controller USB-C port connected to your laptop or your CRN or whatever you like, and send AT commands. You can switch between connections from each port. It also has power switching, so you can actually control the direction of flow of current from each port, or have it bidirectional or completely turned off. Now, the reason behind this design choice was to make sure if somebody is developing test USB hardware, they should have the ability to turn stuff on and off. Considering we have USB-C ports with the power delivery specification, with the latest one, you can have something up to 240 watts being negotiated between each port. And if you're developing hardware, you're testing stuff, I think the developer should have the ability to turn off power if required, or make it unidirectional for safe testing. So that's why we did that. We designed the PCB of the hardware in KiCad 6. It's quite intuitive software to use. It's come quite a long way. Easy to use. I think I would say it's quite beginner friendly. We wrote the firmware using ST's toolchain. We use an STM32 F103, yes. And the case was designed using Fusion 360. So what you can use it for, basically anything that involves you to disconnect or reconnect devices, switch between devices, or actually have a USB device move between multiple hosts. In essential testing automation, that is what we actually wanted to achieve with this product. So with any sort of development, there's always chances of errors, and we have counted a fair share of issues ourselves. So with the first revision of our hardware, firstly, it took 10 days to develop. We sent out the first revision of our hardware after doing 10 days of development. So we received the hardware, we plugged it in, and we realized that the power switching is not working. And we did some few testing, and we realized that the diodes were the wrong way around. So I fired up KiCad again, and I was like, it looks fine in the circuitry. What's gone wrong? So I put the PCB and the schematic side by side, realized, well, the dials were flipped. So the reason behind that was it was a common assumption to be made, right? If you use standard KiCad libraries for the footprint and the symbol, and we just assumed that the pins and pads would align, but that wasn't the case. So we learned the lesson that way, and it was a quick fix. So the second issue we were having was with the USB-C orientation. So as I showed you in my previous slide, that we have USB-C female ports on each end of the switch. So a USB-C female receptacle has CC1 and CC2 lines, but a male plug has only one CC line. And when we use a USB-C to USB-C cable, that will also have a single CC line. So what could happen is you could connect a USB-C thumb drive on one end, and that might have the CC line of that peripheral on one, or maybe CC1. And on the other hand, when you connect the switch to an actual computer, that might have the CC line on the CC2. So we'll have a CC line misalignment, and that would not cause the device to enumerate. So that is an issue that we've seen. We could call it a feature or something that we put in our notes in our GitHub repositories to make sure that when people are using it, they make sure that it might be a possibility. When you plug in a cable one way or the other, it might not work. But we want to actually fix this in a much better fashion, so to make it as plug and play as possible. So we've had, as I mentioned already, that orientation issue is something that we're still working on, making sure that it's as plug and play as possible. And we've already done design review for the next revision, which is going to be the RevC. And so from what you saw in the diagram, the PCB itself still quite a lot looks like a dev board. We have the debug ports and everything on there. We added them intentionally in the first two revisions to make sure that once you're writing firmware, we can make sure every pin is doing what it's supposed to do. But now we're quite confident with our firmware, so we can simply get rid of those debug ports, actually make the footprint of the PCB much smaller, so it looks more of a commercial product. And we also improved the power switching circuitry, the efficiency of it. And currently with the RevBs, we don't do the S-bus line switching, so we can't really get DisplayPort out of the switch at the moment, but that's something we're going to do in the next revision as well. So why did we actually choose to open source the entire project? The reason behind that is Codethink is not really a hardware manufacturer. We saw an issue that multiple automotive clients have had. We've made a solution, and we're like, this thing can actually help many. It's not just automotive clients or people who make automotive stuff. It could be some people who just want employed making hardware. Making hardware, testing, integration from software to hardware, whatever have it. So that's why we made it open source. And at Codethink, we also want to enable better quality and robust test infrastructure. And I think this fits quite well with providing tools to be able to have robust testing infrastructure in general. So what all is free to use? So the hardware is completely open sourced under the CERN open hardware licensing. Firmware, we use ST's tooling, so we can't really call it open source. It's freely available for you to use and then flash on your boards. The case was designed using Fusion 360, so we distribute the STL files for 3D printing, and it's under CC Commons by SW. I hope I said it right. So if you really want to get one of the switches yourself, you can scan the QR code. We have a GitLab that sets you to the project. All you have to do is you go to the hardware project, you get the files, download it, send it to your PCB manufacturer, whichever one you like. Once you do that, once you have the hardware, everything assembled, you go to the firmware project, flash the firmware using an ST-Link, print a 3D, print the case, and to secure your hardware. And there you have it. That's all you need to make a board for yourself. So the bigger picture for Codethink then, this is where does Codethink as a company actually want to go with having open source hardware for testing, for automated testing? What is the bigger picture? So at Codethink, we want to enable availability of safe software, and that is not quite possible without ample testing. essentially. We want to make sure people test their code, and that makes everybody's lives easier. So for that, we want to make tools for testing infrastructure more accessible, which are easy and quick to set up. Because if you have something like that connected to your CI runner, you can simply just plug and play, and there's no more manual testing involved, so it's more repeatable in that sense. And it's quite hard to actually change path of least resistance when it comes to development. We do really want people to not change the way they already make or develop software or hardware. We just want to make sure we provide tooling that makes the existing workflow that they have more efficient. So if we are able to provide more tools in general, it just makes everybody's software infrastructure more better. Maybe it's open source, maybe it's commercial, whatever it is. It does help to improve the existing workflow people have. So that's the motive of Codethink. Provide genius wherever possible and make good testing infrastructure more accessible. So that'll be it from us. Any questions?
It's on, yeah. Just go.
Yeah, the first question would be, and maybe the main question, with regards to the power distribution, delivery, and consumption. So USB-C provides the power delivery negotiation protocol, and if you go to upper voltages, what's the amperage of the board? Will it be able to power delivery for all the output ports, and does it provide the short circuit protection? So like all those problems that you're struggling with in a real testing environment. Thank you.
So in a sense, it's like a cable that switches from one port to the other. So the hardware that we have is suitable for up to 100 watts. So if you want to do power delivery, not the extended range, but the standard range, is capable of that. We've tested, we've plugged in laptops which can do power delivery, which can negotiate to 100 watts of power. That usually does work. But in terms of short circuit protection, if you would like to elaborate a bit on that. So short circuit protection, you mentioned that.
Short circuit.
Yeah.
If I'll short circuit the output port, or if I'll short circuit the output port or input port, does it boil the whole system, or the only port will be switched off, or would it be fried? And what are the timings for this?
So if you have it set up in a unidirectional mode, of course, power is not going to go on the other way around, so it's unidirectional. So in that case, you're not going to fry the peripheral, the host in that sense, right? But again, with any consumer device, if you're connecting two devices together, and if you want to short, it's usually the host that should have protection. As I said before, this device just provides switching capabilities between it's like very much like a software-defined cable which switches from one port to the other. So yes, if somebody wants to really break something, it will break. But then the actual idea is to be able to switch between one port to the other. No, that sense.
So I'll follow up a little bit on that. Yeah, we had some design decisions internally about how much protection should be on there. We've been trying to make something as simple as possible. We could look at a version with some sort of electronic fuse. It's all something we did discuss. However, you are free to take this and add your own if you like. And I mean, if you want to, that's your own thing. This is sort of the beauty of the open projects we're dealing with, is you can take it and customize it to your own use.
And the last question with regards to the power distribution is, it would be really nice having some kind of analog to digital converter, or digitalized, or with a small like the 7-digit screen showing up the amperage, and like it's a simple USB doctor device that you can buy for $1, but it can be incorporated in such a device. It would be really a cool feature to observe. Thank you.
Brilliant.
Anybody else?
I mean, we're just going to follow up.
Oh, sorry. If you want to follow up, yeah.
We did look at
I'm trying
some
to answer. My fault.
basic protection chips that also provided some sort of current analysis. Again, this is something we may or may not do in a future revision. Adding a screen was, I think, a bit overkill. I think we mentioned the price roughly at the moment is about £17.
So 17 quid a piece for Rev B, but again, like in the future revision, we want to make it smaller and get a few bits out of it as well. So that'll get the price lower as well.
Yeah.
The Rev C.
And just reminded me of something of the revision B where you forgot to refill the design files.
Well, yeah.
Yeah. USB tracks don't go very well through solid planes of copper. Yeah.
You mentioned you mentioned the debug port. You want to get rid of it, but probably it's not the best idea for hardware guys, because I am a geeky. I want to see what's going on there. I want to be connected and to manipulate stuff. Thank you.
The thing is, that's for revision C that we're going to do. We'll take it out, but then again, you'll still have access to the previous revisions.
Yep.
So it's all in a Git repo, so
you can add your own ports. I mean, I think if you've seen our prototype, I think somebody basically went, let's put a Raspberry Pi style connector on it, and about half of those pins aren't actually connected. So we could lose quite a bit of space from this board and still have some pins. It's still entirely possible we may leave some on.
Yeah, this is still a functional board. I mean, it will still be always available. So if you make a new revision, it will be more about like having something smaller. So basically doing what is said on the tin. But then again, if you really wanted that, it will all be available for you to order or use or modify as you like.
We have to be a little bit pragmatic about what happens. Obviously, we want to build these for our own use, and we have clients already using them in their test setups. We did also consider adding a second port to allow just switching the power delivery, so that if the port that isn't being used for testing could be used to power something up, just to, say, charge a phone. Again, somebody could come along and do that later. It's not entirely impossible we don't produce a revision 2. So,
I just a quick final question. What would you say? Would you say the overall design cycle time? Like how long from when you're like, we need this thing to you have this thing in your hands?
So for Rev A, we took around 10 days. So first revision, and then again we have lead times on hardware. So it took 2 weeks to come from China. We got that. Then we made a few issues there, fixed it around 5-6 days. Then got the Rev B out, so that's Rev B right there. And now we're going to have a few more days of making Rev C. It was already in process, but then we started in mid-December last year, and now we're early February. So
okay, so 7 weeks, kind of end to end,
yes.
Including having the widget.
I mean, some of that was arguing about open source licenses.
yes,
We actually just published the Git repo, I think, was it yesterday?
yesterday. Yeah.
Yeah, I mean, it would have been a bit silly to turn up to a talk about open hardware without actually opening the hardware.
But you wouldn't be the first.
Yeah, I say there's been some of the development times more been debating about what actual features we wanted. So overall, it's not the worst hardware project we've done. I mean, we've done internal stuff just to make test boards for our customers, and this has been quite easy.
Beautiful. Thanks a lot, guys.
Thank you.